I'd like to welcome you to Lecture 3 of Environmental Science 1401, and we're going to be looking at Chapters 5 and 6 today. And we'll be looking at what seem to be two very different topics, but it's really what we're going to be looking at is sharing the world, and why is it important to protect biodiversity or other creatures as our population keeps growing and keeps using resources. So just for your information, we're going to be looking at these major concepts. What is the status of Earth's biodiversity? Of course, we'll be defining biodiversity, and why should we worry about protecting it, particularly with laws. And please read the chapter on this. Read about these laws, because I'm the person who writes the test, and I know some of them will be on there. And just be able to find those at least in your, in the book, so you can reference them for the test. Also, how as a society do we deal with biodiversity loss? I'm not going to so much talk about it in this lecture, but as we continue the semester we'll do. And then as we look at Chapter 6, we're going to look at human populations and look at a couple of videos that deal with the whole idea of why does our population do what it does, and what do we do about it as a global society about this incredibly growing human population. It's really interesting. In the many years I've worked in environmental science, I've run into many incredible people and had as professors some of the people that you actually are reading about in this book, which is kind of interesting learning about in this class. And I got the chance of working with a fellow named Ed Wilson from Harvard University, and actually worked with one of his graduate students when I was doing research in Colorado. Matter of fact, Naomi ended up taking his job after a while after he retired. But he brought to the forefront of environmental science and biology the whole idea of biodiversity, and the fact that we have to be able to measure it. And eventually you're going to be doing a lab on how do we measure biodiversity. And so to begin with, biodiversity is a very important term, and it helps environmental scientists kind of understand, I hate to say this, but the economical and cultural benefits of having organisms, and not just, from an agriculture sense or a commercial sense, but just what's the value of having trees? What's all these different types of values of nature being what it is and preserving nature? And we're going to look at two types of values. In environmental science, it's hard to promote this because it is a form of ethical thinking that gets outside of the scientific realm sometimes. But in environmental science, we all just assume that there is what we call an intrinsic value to nature. And that just means nature has value in itself apart from human use. And I truly believe, like the squirrels in my yard, as annoying as they can get and destructive as they can get to my house, they have a purpose. And that purpose is not necessarily to benefit me. This is kind of like a biocentric approach, but it is a very important approach to say that we share the earth with other creatures, and we better be aware it's equally theirs as much as ours. Now, as humans use the earth, we use it for what are called extrinsic value. We use organisms as food. We used to use them for mobility, as transportation. Now we use them as pets. We use plants for a variety of resources. We use water resources, mineral resources. So usually what we do in environmental science is we look at the impacts of these extrinsic values of natural resources and try to look at how humans could manage them better and manage them in a way that's sustainable and also in a way that's resilient, and we can recover from a depletion of these resources. But one consequence of human activity is that the big problem we're seeing right now is what we call extinctions and endangerments. Extinction means basically something is totally gone. When it comes to animals and plants and other organisms. When it comes to resources, we'll talk about depletion, which means it's not worth getting that resource anymore. It's either unobtainable, not there, or too expensive to get and just doesn't make life very livable anymore. So we are seeing an unprecedented extinction rate with human population, and as it grows and as we use more resources and take over more parts of the world. And these extinctions are not due to severe climate changes or accidents that we've seen in the past history of the earth, but these are due to us. And we have to be aware of how to recognize them and how are we causing them in the first place. Probably the biggest issue that we deal with as we use nature for its extrinsic purposes is that we are major habitat changers. We modify habitats, destroy habitats, and in turn, when you start taking apart habitats, you're removing organisms or displacing them, you're decreasing the effectiveness of ecosystems, and this can have major effects on biomes. And I've seen this all over the world where we have turned tropical rainforests in Central America, in the Caribbean. I've seen this throughout Asia, particularly tropical Asia, is that we turn forests into farm fields that then lose productivity and turn into literally deserts. I've seen bodies of water drained to turn into land for building, and other areas flooded to make, reservoirs for us to obtain water and electricity. So this is probably the biggest thing that humans do. And guys, a lot of organisms, like we mentioned before, beavers can change habitats, but not in the way that we do. So this is one of the biggest factors of how we create biodiversity loss. And particularly when we look at urbanization, what's really scary as you go into this earth, we're going to see an incredible shift towards urbanization, where again, by 2100, we're going to see a world that is almost all urban and very little land for agriculture. A lot of deforestation, that means removal of plants, particularly going on to accommodate for urbanization and the diminishing places to grow crops. Another thing we do is, by removing habitat, is we fragment habitat. That means we take a big area and we might put buildings and we might put roads and other stuff, and we slowly change nature and build and do things. Looks like I'm playing tic-tac-toe here, but what we do is we leave these green areas behind that are still natural areas that are now disturbed, and they end up becoming what we call fragmented or segmented. And this sometimes makes it difficult for animals to live in these areas. It prevents them from breeding throughout the area. You end up with what's called inbreeding, or sometimes bottlenecking, and it prevents the animals from basically going from migrating to find food and for their young to find new territories. So this is a big issue for us. And I've seen case after case where, particularly in the Native American communities, they're trying to restore their the animals that they value and hunt and use, and the plants that they use, from being segmented and fragmented to the point where the animals literally cannot move from one place to another to breed, or these animals can't follow migration patterns because of highways. And I've seen some beautiful projects where near reservations, the Native Americans are encouraging the government to build walkways over these highways and corridors that sometimes go underground to allow this fragmented land to be utilized by the animals. So what else do we do with our anthropogenic activities? We tend to sometimes overexploit our resources, and I can't understate this enough, particularly in a country like the United States, where we have a huge per person footprint. Now, as a country, it's big, but not that great. But per person, we have one of the worst of the footprints. We probably use 17 times more resources than if you were to average out everybody else in the world. And that also means 17 times, more access to food. Now, don't say, wow, we don't eat 17 times more than other people. No, we tend to waste parts of food. Like when I was living in Asia, man, we'd eat fish heads and stuff like that. And you actually, as a kid growing up, we would, my parents were kind of like equivalent of developing nation people, and we would, no part of that animal or plant left the house. You ate it in some form or used it for something else. And today we're very wasteful, and that means if we're wasteful, we can end up throwing out 50 to 75% of our food. You're going to see a case study on this, an interactive case study. So we tend to overexploit, no matter what that resource is. In this case, we could overfish, we could dig out too much oil, too much coal, we can use too many minerals, particularly with the growth of electronics. We've seen an unprecedented demand for petrol to make plastics, and mineral resources to make electronic devices, circuit boards and all of that, silicon chips. Another thing that we do is we're very good at introducing invasive species. An invasive species is any creature that gets introduced either through a natural phenomenon like it's blown 1,000 miles away by a hurricane or something, or it's introduced usually by transportation or through the pet trade or through smuggling for some case, like we're using animals for whatever, certain types of illegal purposes or unethical purposes. So invasive species are incredible because these are creatures that are introduced to a new environment, and if they're lucky, they will take over that environment and displace local species. Now, sometimes that's good, sometimes that's bad, actually. For the most part, it's bad because it does destroy the natural habitats or displaces the other creatures in those natural habitats. So when we look at these invasive or non-native species, guys, it was funny, the first time I did some consulting overseas, it was close, it was in Jamaica, and I was just walking around one day admiring the beauty of the island and all the plants that I thought were native. And after talking to some of the one of the botanists there, because I'm definitely not a botanist, I don't know plants that well as far as identifying them, but that person told me most of the plants that were growing supposedly wild there were from India and from Asia, and they were introduced during all the slave trading and the rum trading and all of that. And these, so much of Jamaica's beauty, which Jamaica sells to the tourists, is not Jamaica. It's all invasives, and that's a lot true for our country. Most of the plants around us don't belong, but it still contributes to a biodiversity. So we end up with a new biodiversity rather than the original one. And that is not good for the creatures around us because it changes all sorts of things. Like water availability, sometimes pests control and other things like that. And the photo here is very great because this is one of my favorites. I actually wrote a little case study on this, which I can give you if you want. So kudzu was an Asian vine that was controlled in Asia. It had pests, other creatures that ate it, and climatologically, it was controlled in its growth. You let it loose in South America, and it will cover a house. If it is not trimmed, it will cover a house within a couple of months. It will cover cars. I've seen buildings being covered and whole forests being covered by kudzu. Once we took a family drive from Houston to Hilton Head, South Carolina, and we just saw fields of kudzu that just choked off everything, including just encapsulated houses, and literally had cars buried underneath it. This is what invasives can do, and they are very destructive to what we call the southeast piney woods and wetland areas, and are changing those ecosystems and that type of biome. What else are humans good at? This sounds like a bad list, but we're also good at damming waters, damming rivers to build aquifers, so we have water available to us in reservoirs. We're good at depleting water from certain areas. We're also good at producing a lot of wastewater that goes out into oceans, and it causes a decrease in what we call the salinity of the ocean, and that can kill off things like coral. A lot of freshwater output could also cool certain bodies of water. And another big thing we do, thanks to our use of fossil fuels, is climate change. And climate change could also be affected by urbanization. It's called the urban heat island effect. When you get into major urban areas next to a wooded area, the urban area can be sometimes anywhere from 10 to 40 degrees Fahrenheit difference in temperature. It means hotter in temperature. In climate change, we also see more extreme changes in climates. It means certain areas can get warmer and wetter, other areas warmer and drier. Some areas colder and wetter, or colder and drier. So this is a big issue. And anytime we change air temperature, this significantly affects also ocean temperatures. And we're seeing this right off in the Gulf of Mexico, in the Flower Gardens Banks National Marine Cemetery. I'm seeing this a lot because I'm on a committee that meets quarterly to talk about this. And I've been over to the Flower Gardens to do research using a underwater sub, a remote sub, to look at this. And the warmer temperatures of the Gulf are killing off corals, besides producing larger hurricanes and more numerous hurricanes. And the corals are basically support all life, not only in the Gulf of Mexico, but creatures that come from literally all over the world to breed and feed and to take advantage of the corals. So when we start altering local biodiversity and climate change, it can have incredible impacts on an area and on the world. So why care about biodiversity? Because I know people that think, if everything was a city, that's fine. If we get rid of all animals, we wouldn't have mosquitoes and other stuff. But the thing is that we have to understand is that in environmental science, it's very difficult to tell politicians that we need to protect nature for the sake of nature, and we really don't have the right to be using nature the way we do. So we have to find some what we call instrumental value to creatures. That means what is their usefulness to us or their extrinsic value to us. Okay, because you can't sell everybody on intrinsic value unless that is your ethical system. So what the United Nations does, what other entities do that help to set regulations on how we use resources, and particularly biodiversity, we go in with the understanding, I am doing this for the intrinsic value, but I have to give the public instrumental value to justify preserving this and that. And your book is full of all sorts of examples of this I'd like you to read. So what instrumental value and even intrinsic value tells us is that to build an argument for saving nature, we came up with a concept called ecosystem service. It's funny, there's a company called Ecosystem Service and they clean toilets and clean buildings, but this is a little different. An ecosystem service means if I was to lose this ecosystem, how would that affect my lifestyle? Now, yeah, there is an intrinsic value to losing it, but that might not affect my lifestyle unless I go to visit this on holiday all the time and I go camping there. But what is its economic value? And what we have to do is take the intrinsic value and find some type of thing that is economically obvious. And it doesn't mean, well, these trees here are useful for paper or wood. No, these trees here might produce compounds or might produce enough humidity or might take up water that it improves the quality of the area. It prevents flooding. I mean, we know trees can prevent flooding by taking up water. They also purify air. They also moderate the temperature of an environment. They act like air conditioners in a way. So that is taking something that we know is important, a tree just in itself, but saying without that tree, we can go to heck real quickly. So we have these ecosystem services that are sometimes very subtle. Sometimes we don't see them, but we have to find a way to add value to everything. It doesn't mean I'm using the thing. It could also mean if that thing was gone, can that affect the earth in a way where we have more flooding? And when you look at Houston area, particularly, Houston in the 40s, 30s and 40s was mostly green. I've seen, not so much photographs because there weren't too many aerial photographs back then, but maps that were made from that period of time where Houston was just so incredibly green. And now you look at Houston today and it's just big areas of cement and buildings and whatever, and the green is almost gone. And that has caused, urban heat island effect. It's caused flooding problems because there's nowhere for the water to go. The trees don't remove the water. There's no soil for the water to drain, and it just runs off into these artificial rivers, just like what happened with Harvey and every other storm that comes through here. And so that's an ecosystem service for maintaining a lot of vegetation. And we are trying now in Houston to put green areas in here and disperse it in a fashion, even on top of buildings, to try to bring back some of the ecosystem services of the wilderness that was here before. So one way our country approached ecosystem services, and this goes back to Teddy Roosevelt, early 1900s, we as a country enacted, national parks. and coastlines. Today we even have protected coastlines. A lot of this was done not really to prevent us from using nature. It allows us to use nature in a prudent way, that whatever we use, we somehow put back, or we accommodate, or we're careful how we use it. So a lot of the national parks, would you think, were set up just to put land aside to not be used? But I don't mean just recreation. I mean, we are allowed to use the trees in national parks. We are allowed to cut those down as long as we replenish them. Matter of fact, the national parks were set up so that we could have wood available for construction and for running railroads. When railroads needed wood ties to hold the tracks together, and railroad cars are made of wood and they burn wood. We still need wood, but luckily a lot of it doesn't need to be harvested out of national parks today. Even some is done too. We protect coastlines so that we don't overfish them, or we allow only certain people to benefit from the fish in that coastline, to protect it and to make sure we don't overuse the resources. So yes, we're allowed to use national parks for lots of things, even to drill for oil. What it does is it protects that oil for future use. And this is why a lot of presidents keep looking at Alaska, because Alaska is sitting on a lot of stuff, diamonds, gold, oil, but we're keeping it in reserve just in case. We're putting it away to protect it. And that's a lot of what protection does. It doesn't mean we're not going to use it, but it means we're going to use it in a prudent way and hopefully not deplete it. Or if we do take it out, we still maintain that environment where it is, particularly for the intrinsic and for the recreational value. What I probably least like about environmental science is the terminology. And you will too. And we're not even scratching the surface with terminology. So when we start talking about protecting things, you better be very careful what you say, because people will figure out real quickly what you do and don't know. And when you come into this class, you'll know. So there's two ways to protect nature. One is by conservation. That means that we are setting up a protected area for limited use. And if we do use something out of there, we do it sustainably. That means we make sure that that resource is replenished. Then there's preservation areas, and we've discussed something like this before, where this is an area we leave alone, you don't touch. And there's one near Freeport, that's one of our closest ones, that's an untouched area to represent that wetland, that coastal wetland wilderness, which at one time made up a lot of Texas. A lot of our wetlands, particularly like the prairie wetlands, salt wetlands that used to be Galveston. And we have people that preserve those too. That means they can't be touched forever, and sometimes get 99-year leases that go on and are renewed every 99 years to the end of the world. So conservation and preservation are two different things. Conservation is easy to justify. Preservation, you better have money to back it, and you better hope that you can keep reclaiming that preservation area over and over again. So these are two very important concepts when we look at protection, and we have to use our terms very widely. Okay, and some things, when we want to conserve and preserve them, it creates some issues for people, and this is particularly true for wolves. When we start looking at wolves, people fear wolves for their own safety, for safety of agricultural animals, pets, and when we start talking about reintroducing them and conserving them and preserving them, this brings up a lot of emotion, particularly in wilderness areas where wolves can do personal damage to people. So when we start looking at conservation and environmental sciences, there's a lot of emotion that goes into what we protect and the consequences of that, because no one can guarantee a safe world. Okay, and nature, yes, can be dangerous. Probably mosquito bites cause more death and harm than any population of wolf can. So please understand this. And part of conservation and protection too now involves, in the newer model of doing this, is making sure that we have access for animals to migrate through these protected areas from one to another. And this is a very difficult thing to do. And it's very expensive, and it's inconvenient sometimes, particularly to have underpasses and overpasses going over highways and having to sometimes reroute highways or build areas that don't cut off natural areas. Have these what we call corridors that run throughout cities. Guys, and this is a very important part of your book, this figure here in chapter 5. It gives you all sorts of ways that governments could approach conservation and preservation. Governments can take over land. We call it eminent domain. We can have land trusts, and I helped out with one at one time. Basically, we would raise money to buy plots of lands from individuals or have people will their lands over to us, and we put that land into a preserve. Sometimes we turn it into a conserve or a conservation area. There are what we call conservation easements. Houston is doing this a lot because we learned once we don't have conservation easements, that means green areas, these areas flood and we lose a lot of ecosystem services. So now what we do is we can build areas, and you can see all the green areas here, green spaces, trails, whatever, that protect what's left of our natural environment. Okay, we can do what's called tradable development. That means if I'm going to go in and tear down a green area, you see this a lot around us in this area. If I'm going to tear down this green area and say I want to build a housing complex in here, we will go along and nearby find a way to replace that, either nearby or somewhere distant, to maintain those ecosystem services. A lot of times when the construction goes down, the animals will find a new place to go. And that's what we try to do with this tradable development rights. And then what we can do is payments for ecosystem services. And this means that if you're a country and you own a jungle, you can actually be paid to maintain that jungle for the resources that that jungle provides in a sustainable way. So you have to be careful. This is a very difficult thing to do. And a lot of time, this is done particularly for what's called carbon rights. That means plants take up CO2, they produce oxygen, and places could actually rent their forests out for companies that want to pollute and produce CO2, and you can say, well, my forest soaks up this much CO2, so you're going to pay me for my forest to do that. Because if you don't, I might have to chop down my forest or whatever, blah, blah, blah. And you can't just do that to 20 different people. You have to apportion your forest and say it's doing this and this much CO2 removal. So it's a very difficult thing to do. And that's what these two chimpanzees, I'm sure, are discussing right now, the financing and cost of it. So there are various ways we could approach conservation besides just saying we can't touch anything, which is more preservation. And we can do preservation too in this, particularly when we look at ecosystem services and what land trusts can do for us. So for the test, please read the chapter or go through the PowerPoints, whatever. It's probably just easier to read the chapter. Read the chapter summaries. Look at some of the major topics in each of these chapters. Because now what we're going to do is jump from the creatures that we're disturbing and what's the consequences of our population doing that. We're also going to look at populations of creatures too, because we have to understand when we're removing creatures from an environment, how does that affect their population growth and their survival? So when we look at humans, my gosh, we have about, 7 to 8 billion people right now on the earth. And that's a lot. And we are growing more and more. Our population is doubling over a very short period of time. And just read about the rate that we are growing in your book. So we are experiencing doubling rates of our population that occurred nowhere else in history. And guys, that means every time the world's population doubles, we double our resources. And as a country starts becoming more technological, that even further exacerbates this, because as we become more urban, we use much more resources per person than a person living in a jungle in a developing country, or in a field in a developing country, whatever, in a desert, whatever the conditions may be. So along with this lecture, you're going to have an activity to do related to Thomas Malthus. Thomas Malthus was not the first person to recognize that human population is growing and has impacts and blah, blah, blah. We've recognized environmental pollution years ago, many years ago in earlier civilizations, and particularly around the time of the democratization of Europe with the Magna Carta. pollution and wastefulness of land use was recognized back in the 1200s. And other countries have even done that before that too. We're mostly familiar with European history on that rather than that of other countries. But Thomas Malthus, here we are during the technological revolution, the first one actually, where we started using things like petrol. I shouldn't say petrol, but fossil fuels to run society, and we're able to build these huge urban areas. Malthus started noticing that human populations were on the rise, and these population increases were exceeding resources. Particularly, he was focused on the economics of food. So Malthus warned early that if we keep growing, we're not going to be able to produce enough food eventually, because food increases at a very fixed rate, whereas populations increase at what we call an exponential rate, and you'll learn about this a little later. That means our population goes through doubling cycles, but food production does not. And even today with modern technology, it's still too difficult to keep food supply up to our burgeoning population. What we're doing now as societies is eating all sorts of unique and weird food, which is why you hear about all these diseases coming out. We're eating foods we've never did before. People are hunting foods and growing, cultivating animals in close captivity, and their diseases are spreading to us. Another thing that Malthus noticed, and this sounds kind of horrible, is as we provide ourselves with more sanitation, and people are not dying as much from particularly infectious disease, but also diseases related to hard labor and stress, we are seeing humans are growing even more so, because not as many people are dying as are being born. And we'll learn these concepts a little later in this chapter. So fast forward from Malthus to Dr. Paul Ehrlich. I actually had Dr. Ehrlich as a professor when I was taking graduate courses in Colorado. He was actually at Stanford University, and he had research going on in Colorado over the summers. And he really affected my life to the point where I was a proponent of what's called zero population growth, and only wanted to have 2 children, and was kind of lucky to have a boy and a girl. Because it's nice to have one of each. And we did what's called replacement value. That means my contribution does not double the population. It just replaces me and your mom, or their mom and I should say, to be polite. So Paul Ehrlich was sort of like the newer generation of Malthus, but he started seeing the Earth's capacity depleting faster than what Malthus saw, because our resource uses went up, our caloric content went up, our wastefulness we were more wasteful with foods than we were, and our crops changed in nature to the point where we use much more wasteful crops in general. So he wrote a book called The Population Bomb, and because I had him as a professor, we had to read it. And he did have an updated book of that too later on. Okay, we read both versions. Okay, so whatever. But he predicted eventually a doomsday where all the world would end up in a population collapse because of starvation. And whenever you start getting starvation, you get malnutrition and disease. And then you get war and strife and stress as a result of the lack of those resources. Now, he started a whole he actually fueled the doomsday cult that was already there, but he provided some of the science behind it. And he's a very compelling person, to be honest, and he had data from his own research on animals to support this. Unfortunately, his data on humans didn't take into a lot of account anew the technological revelations that occurred in the 80s. But for the time, he was accurate. And it was funny because Dr. Ehrlich lived the way he preached. He was very simple in his resources. I remember his little old Volkswagen bus that got very good gas mileage, and the thing was older than half of us, of his students, whatever. But he started promoting prudent ways that our population can grow and not create strife. But also he proposed that we should control our population to prevent this horrible collapse and just control it, with the idea of zero population growth at the time. And ZPG organization, which followed his guidelines, today exists as something called population connection. So there are still groups out there that promote not just 2 children per family, because that's not everybody likes that, but also how do you teach your children to become better resource users so that there is a future for their children and there is a sustainability. So Ehrlich started a lot, particularly in the United States, and has tore out all over to other countries eventually as his book went global, and was adopted by other groups and promoted by United Nations and various environmental scientists. So how do we get biodiversity? How do populations survive? When we start looking at the characteristics of populations, we have to pay attention to 3 things on how the creatures you see outside get here, or the creatures inside get here, inside your house. So we have 3 terms we need to know. One term is called natality, and this is a measure of births. One way to measure natality is birth rate, and that means the number of organisms born per 1,000 individuals a year. Now, this definition of birth rate can vary depending on the organism. Like with bacteria, we can't measure per year because they replicate sometimes every 15 minutes to every day. So we can do it in a shorter period. And you look at some trees and plants that don't replicate for 100 years. So this is relative. But the thing is, we always do it as per a certain unit. And this gives us a handle on the relative amount of growth related to the population. Because some populations grow rapidly, but it's a small population. Large populations, if they grow rapidly, that's a problem. That's not true of a small population. Another term is mortality, which means basically death, from the term mortis, like rigor mortis, okay, which means stiff death. So we have a unit called death rate, sorry. And that just means the number of organisms that died per 1,000 individuals per year. And we can monitor the growth of a population by mathematically calculating mortality and natality. And we can see if that population is going up or going down based on our measurements. Now, we can do this as a lab, but it's very complicated. And the math can get a little tricky. But if we're, appreciate that this is something that's not hard to measure. The math might be a little tricky. And then something your book left out is something called morbidity. And that means the number of illnesses in a population. Because illness is a major factor that can contribute to mortality or natality. It tends to increase mortality and decrease natality. That's increased mortality, decreased natality. So this also has to be taken into account. So we look at disease individuals. I did this as a job in New York City for a research lab that was on the grounds of the New York Aquarium. So I'd go into work, slip by the tourists, walk over a couple of shark tanks, and I was in my lab, if I didn't take another shortcut to get in there without having to walk over the shark tanks. But I researched for a guy the number of parasites that were found in fish and how that could affect the fish population. So these are 3 very important measures that environmental scientists do a lot. And we could also do it with humans. We could look at how fast the human population is growing for a country and how it, certain things like sanitation, how even individual rights, how poverty, how income affects this. So what's another thing we look at in populations? Today, the big thing is we do what's called genomics. That means when we're looking at organisms and birth rate and death rate and mortality, we look at genetics of literally the population and even almost all the individuals we can catch. And if something dies, we will, let's say 100 things die. We will look at the genetics of those things and see if a certain genetic type represents the population more. Just like what happens with the flu and with COVID-19, is certain people have mortality or morbidity. and we can look at 100 of the people that die or 100 of people that get very severely sick, and we can look at their genetics and say, wow, people with these traits, they're the ones that are really getting sick and dying. So we got to pay attention to their part of the population. So once we look at a population, we dig down deep inside. At one time, we used to look at the protein composition of the animals. Now we, and plants and bacteria, whatever. Now we look at, and we used to just look at the appearance, like in this picture too. Now we can look at the genetics. And here's what we learned, is that when we start looking at bears, and you see, let's say, a brown bear and a black bear, they are the same species. They are the same thing. I mean, they interbreed, they do whatever, but when you're counting them, usually what we do is we would count them as a subset. So we say, I found 100 newborn, and 40 were these, and 60 were these. And that might be true in one area. Then in another area, you might find the reverse of that. These have unique genetic differences called mutations that can have survival value in a particular environment. And not just like hot and cold or stuff like that. It could be the type of food. It could be other factors in the environment that allow more of these children to be born than that, or that encourage more of them to die than them, or encourage them not to find as many mates as them. So this is what's neat. And guys, we do this with people. And when we start even looking at ethnicity of people, this is important, and we're learning this with many diseases, that some people are more susceptible to disease than others. So if that disease gets into a population of people that are susceptible to that disease, that is important information to know. And in this class, I wish we had the ability to go out and do genetic analyses and do these type of studies where we can actually calculate how many creatures will be born in a certain environment based on their genetics of a particular species, what we call the mutations or the variations of the genetics. So what do we do with all this information about natality, mortality, morbidity? What we do is we draw graphs. We make charts. We record it. And what we can do with different types of animals is we can look at how their birth rate goes along with their death rate for certain individuals in the population based on age, based on gender, based on genetics. And we can come up with all sorts of calculations and tables. And believe me, I've done this, and I would never torture undergraduate students with it. This is horrible, but I actually worked on a project where we were trying to teach this to college freshmen, and it didn't. I mean, we think we taught the students, but they weren't happy with it. A lot of math. But anyway, we can come up with a measurement called, or representation called, a survivorship curve. That means in every population, you can take mortality, natality, and for each age group of an individual. And there's important steps when we look at the age group of a population. We look at the very young, who are the most vulnerable, those that are being born. We look at the equivalent of puberty. That means, when is that organism reproducing? And then we look at the ages where the creatures start becoming weakened and more susceptible to death. And then we look at the organisms in which they have their maximum death. Just like with humans, it's anywhere from the 80s to whatever, 100. So what we discover is we can break creatures down into 3 categories. And there's in-betweens on this. It's just that these are 3 extreme categories. Creatures that have high mortality of young, creatures that have high mortality across the spectrum. That means young, middle-aged, whatever, teenagers, whatever, older people dying. And then we have species like ours, where really most of the deaths are occurring at old age. Doesn't mean other groups don't die, but it means that the rates are different. And the next slide will show you that. So this is a graph called the survivorship curve. And if any of you don't know this, I'm going to teach you the riddle of the Sphinx. In Egyptian culture, the Sphinx was supposedly a guardian. Okay, and if you walk past the Sphinx, you had to get permission to walk past him or to go near him. Okay, and or her, whatever. Okay, and the Sphinx had a riddle that if you pass, you can go by. And the Sphinx says, what walks on 4 legs when it's young, 2 legs when it's grown up and 3 legs when it gets old. It's 3 legs when it gets old. And if you didn't know the answer, you were eaten or thrown off a cliff or stomped on. Okay, I've heard variations of the riddle. Okay, and it's people, like what's shown in the picture. I think that was done kind of purposely for the riddle of the Sphinx. But anyway, let's get back to the darn class. So we have what's called a type 1 survivorship curve. And these are creatures like us, like a lot of large animals, like a lot of certain types of plants that live a very long life, and they keep living, and very few individuals die. And then all of a sudden, the population at a certain age group just taper off and they're all dying. This is called type 1. And what's neat about type 1 creatures is that when you look here, everybody's kind of valuable, because what you're relying on is kind of like a smaller population that it has to live a certain age to reproduce to keep that population growing. So for your population to be able to grow, you have to live through this period of having kids, taking care of them, because once you get this age, the last thing on your mind should be reproduction. So if you don't make it to this age, you're gone. Or so something comes in and wipes out this kid, because this kid is going to make that reproductive population, almost all of them, you can severely decimate that population. And this happens with like the fisheries industry. Tuna can live up to 60 to 100 years. So can lobsters and a lot of other commercial fish. So if you start capturing, animals when they're young, there's only so few young out there that can contribute to the population. And you're wiping out this group here that makes this group, which makes the whole future population of them again. So that's a problem. And believe me, people that do fishing industries, they're well educated. I have 3 friends, one good friend, his significant other runs a restaurant with him, and he runs fishing boats. Okay, I shouldn't advertise, but there's a place called Katie's in Galveston. He's also a sustainable fishing person too. But he sits down and calculates how much fish he can catch of a certain age group to allow that population to maintain itself. And a lot of the fishing industry does that. They have quotas and timings, and they have to bid so that they don't deplete the ocean, particularly for these type 1 fish, where we're going for very big, mature fish. And sometimes what we have to do is hunt the fish when they're at this point in the non-reproductive stage. The problem with that, the fish might be very big. I mean, some tuna get to be about the size, they get huge, almost like the size of a car, some of these fish. And the same is true for lobsters, but the flesh might not be as tasty. And the fish might accumulate pollutants in their bodies. Then there's something called type 2 growth curve. And these are creatures that over time, you have an equal chance of dying as a mature adult, a teenager going through puberty, an egg, or an elderly adult. So this is called a cohort. That means 1,000 children start out, or offspring, and they live and live and live, and their population drops. And this, every time you go to a school reunion, there's less and less and less. Here you go to a school reunion, so it's the same damn people you don't want to see every day until about here, and then all of a sudden you're the only one at your reunion eating a cupcake. These type of creatures are the easiest to manage, because no matter where you pluck them from, it's okay. You can manage the population pretty easily. Now, then there's what's called a type 3. And that means that of 1,000 individuals, most of the babies up to maybe the first year, first week, whatever the lifestyle of this creature is, almost all the babies are dead. The population goes from 1,000 to maybe several hundred. What am I saying, several hundred? A few. That's a problem. But that's worked into the system, because once those individuals do make it, the population is stable and goes on, and they carry out the next generations. And these organisms tend to produce dozens of offspring. hundreds of offspring, sometimes tens of thousands, billions of offspring. These don't because they don't have to. The babies live forever. They produce a moderate amount. They produce the most. So a typical oak tree over its lifetime can produce billions of individuals, and all you need to live are two. Oysters. I grew up with oysters. We used to collect oysters along the coastline and eat them, sometimes raw, which was stupid, but always with either Tabasco sauce or horseradish, okay, depending on what your inclination was. So oysters, over their 60-year lifespan, they can have millions and millions and millions of children. And those millions and millions and millions of children, only a few are left behind. So guys, what's neat about these organisms here, you better not take those adults out of the ground, because they're the only ones left of millions. And we got to be careful, because you remove one oyster, one tree, you're removing billions of offspring that are now not showing up in a cohort. And that means that that cohort, all of them can end up dying, because you're removing for each one organism billions of offspring. Here you remove one adult, you just remove one child that can make it. So when we deal with fish like this, a lot of the fish that we eat, particularly shellfish, fit in this category. So we've got to be careful how we harvest the adults. We have to harvest the juveniles, which are sometimes not as commercially cool. You don't end up with big fillets. Whoopee. It also has to do with how we manage resources. When we start cutting down trees willy-nilly, that forest might never come back, because there's not enough individuals for thousands to die in one generation if there's only hundreds there, because they will all die off. So this is how you use this information. And we can look at even genetics within these curves on who tapers off first, what genetics, who has the fastest decline here, which of the babies that are dying the most, and look at all sorts of factors. And this is the beauty of environmental science. Okay, another way to look at population growth is by looking at another aspect of reproductive strategies. So you're going to have this term called K and R strategies. K means carrying capacity. That's the German spelling out with a K. And it means these organisms maintain their population to the point where they've maxed out their resources and they don't produce any more offspring. R strategists live in low populations, but they produce lots and lots of offspring, use up their food, and then their population goes back to a normal thing. So when you look at them, they tend to have a type 1 curve. They will have a type 3 survivorship curve for the most part. So please read about this, because guys, when you start looking at how we harvest and use creatures, that means crops, whatever, you know, even as crops, we grow crop plants that are certain strategists. And if we're not careful managing them, we can lose them too. So we have to be careful how we manage these. And also when we do environmental damage, you know, these creatures can suffer differently than these creatures when environmental damage takes place. These creatures suffer when you're hurting the adults. These creatures suffer when you hurt the juveniles. And this is and I have case studies on this, but you'd rather not again do the math on these, because you're looking at each individual and its strategy and trying to figure out who is more susceptible to dying and extinction within an environment. So K strategists tend to like stable environments. The organism is usually large, will learn. They usually have a type 1 survivorship curve, so their length of life is very long, and they live particularly to the point of reproducing. They have a small number of offspring. Don't worry about primary limiting factors. We'll cover these a little later. Okay, and here's some examples. R strategists, they usually live in unstable environments. And we will one day take a virtual field trip, and I will show you R strategists and K strategists and how they inhabit environments. These guys tend to be small, short lives, because most of them die as a juvenile, and their adulthood, they don't always live too long, except for oysters and certain ones. A lot of these guys die very young, sometimes within a year for R strategists. They don't usually have parental care, and their growth rate is very quick, but also their death rate can be very quick in juveniles. And you can see here mosquitoes and what are called annual plants fit that category. So guys, we're going to be coming back to this, a lot of this, and use this stuff. But this is part of understanding when you go into an environment and use it, or when humans are changing their lifestyles, how does our growth characteristics and disease characteristics affect us? And this is kind of a scary prospect that some people look at disease and say, we need to have it around because it is a major factor in controlling population. And maybe we shouldn't provide sanitation for areas and health because once you start providing resources for people that allow them to live longer and the children not to die, that can cause burgeoning populations. And that is an ugly, ugly thing to say, but it's on the minds of people. And it's sometimes how we manage populations. We see this even with our pets. As we keep our pets disease-free, they live well beyond their lifespans and produce more offspring. This is true of invasive creatures. If they enter a new environment where there's no natural enemies, no diseases, their population bird takes over and they can displace all sorts of creatures, displace habitats, replace niches, and that affects biodiversity and changes biodiversity. Now, the graphs you're seeing here, which look like a bunch of Jenga blocks or something like that, these are ways that we can graphically depict what's called age and gender population curves. These are not just used for humans. These will be used for animals. And I've seen these used for animals when looking at populations of animals for whether populations were in danger or not. So what this graph does is it kind of takes our survivorship curve and puts it more into, I don't know what you would call this, but a different type of graph. So we can look at pre-reproductive. That means these kids are just getting older, but they're not making babies. This is who's making the babies right here. And these are the post-reproductive. That means you're sitting around watching TV or playing card games, because right now you're too old to play video games, whatever, and they're not making babies. So what we're going to be concerned about when we look at these graphs is this part right here. How big are they compared to the bottom? Because the top we're not going to worry about too much, because if these people are dying off like crazy, who cares? They're not contributing to making babies. They are contributing to using resources, though. I'm in this category, believe me. So I'm the ones that you want to put on a boat and burn and send out on the water. So when we look at what are called age distribution curves for animals, humans, whatever, we look at this and we can tell whether this population is growing rapidly, stable, or declining. In this case here, okay, the first case here, look at this. When you see a triangle like that, it means that these kids here are entering here. And this population, okay, is going to keep moving up slowly and slowly and eventually increase this population. So what the heck does that mean? I just confused you. You see this? If these kids don't die, they're going to move up to there. And that's going to be that big. This is if there's no deaths. There were deaths there, obviously. If this moves up to here, then that becomes this. And that population goes up. So this population does have a fair amount of, a lot of people don't make it to old age, but the bottom is bigger. So when the bottom part here is bigger, it just means that bigger moves up and that number of people goes up. And guys, I know that's confusing, but just remember, if it looks like an Eiffel Tower or a pyramid, that's a sign of a growing population. It takes about 1,000 times to look at this and say that this 3 million, if it goes up to here, that means that there's will be 3 million people here instead of going down. So if we see this bottom getting bigger in proportion to the top, that's a rapidly growing population that could be doubling every 10 years for all you know. Now, this is more like the U.S. and many countries. If your bottom and middle are about the same, okay, that means your people are not dying, but you're not really increasing the amount of young that are making this population. You just don't want this bigger than that and moving up. So this is a stable population. So let's say if I'm just built like a square building, I'm okay. Now this one's a declining population. And that means if your bottom is smaller than your top, look, that means that this number of children are making it here, and there's not going to be that many here, and not that many here, and not that many here. And that means there's less to reproduce, and then this gets smaller. So if your bottom is smaller, this is a declining population, and not from animals or plants or humans leaving, but of just not reproducing. And this is funny because this is typical of Italy. This is actually real data from Italy and Japan. We're seeing this in other countries now. Scandinavian countries, the populations are dropping to the point where the governments are like, we can't find workers. And why are people not mating? It was really funny because I think of Italy when I was in Europe as the land of love. But definitely is not showing it down here because there's less babies being made than the people that are making the babies. I mean, when this is larger than that, that means less people are making babies. Look at this. More people, fewer people are making more babies. So they're making more babies per people. They're making less. They're making about the same. That's a problem. My mom's country of Hungary is worse than Italy. But we always have a joke about Hungary is that we lost the book on how to have babies. Just like the old joke of we don't have ice in Hungary because we lost a recipe. Okay, so this is a problem that we see for countries. Now, it's not a problem for the world because the world's saying, wow, human population is dropping. But when you're looking at building economies and keeping the structure of your country going, this could be an issue. And we can look at this in animals too. Remember that. We can see if a population of animals is growing rapidly. If it's an invasive, that's bad. If it's stable, which is a good thing, or if it's declining, because those could eventually decline to extinction. And this isn't science without a graph. And you're going to learn about this again in a video. That's why watch the videos. Okay, so the way we study populations is we look at a hypothetical situation that's called zero, time zero. This is called reproductive cycles. Don't worry about that. This is time, and it varies with the creature. Or we can even put number of generations here if we want. First generation, second, third, whatever, on the x-axis. The y-axis is always going to be the number of individuals we're counting in that generation. So if we start with 2, if it's a sexually reproductive creature. If it's not, then we start with 1. And we say, go at it, boys. We just see that initially, the population doesn't really go up real quickly. Because everybody's getting to know each other, they got a date, they got to, get some money, go out, whatever, and it takes them a while to get used to mating. And then the number starts increasing. But this initial period is called a lag. And this is true when any environment gets destroyed and we try to grow it back. There's a lag in the growth. And then the lag, if everything is right, that means resources are perfect, the birth rate is exceeding the death rate, then you get into what's called exponential or log growth. And that means more organisms are being born than are dying or getting sick or whatever. And that increases incredibly. That is a maximum growth rate under ideal conditions. So we tend to see this after a while. And then things occur. As your population increases, a lot of creatures are discouraged from mating. They find it harder to find food, territory, places to live, whatever. Competition for their niches sometimes because there's so many around. Disease tends to take over when populations grow rapidly. And the death rate now starts getting higher to the point where it eventually equals or fluctuates with the birth rate. Because this is not a straight line. This goes up and down depending on fluctuations in food and birth rate, death rate, disease. And you have now what's called this stable or sometimes dynamic equilibrium, depending on what you want to draw here. Dynamic means up and down, stable means a flat line. So most populations reach what's called an equilibrium. That equilibrium means that's the maximum number of creatures that can be in that population before resources, disease, or just overpopulation in general drops that population down. And then, of course, what will it do? Start over again and curve up and whatever. So this is called a population growth curve. And I purposely give you the reference. Look it up in your book. This is very important to understand how environments recover, and when we capture creatures to use for food, what is their growth rate and how does it recover at what rate? We can also understand the spread of disease with this too. Because guys, something like flu, coronavirus, infectious diseases have a growth curve of their own that we can see how long it takes them to replicate within our population. So now I'm going to start ending the torture, and let's take now that exponential curve and put it into a pretty picture. So what keeps a population flat? And again, flat can mean like this and like that. It just means that it's a certain number over a certain period of years. So when a population reaches its peak, that means it's at its point where you can't have any more births than deaths. You reach what's called carrying capacity. And carrying capacity has what are called environmental resistance or limits to it. Limits by the environment. Okay? And you will see lots of questions about this on the test. So for example, in fish, what keeps fish populations down in the ocean could be things like oxygen level. Guys, I've seen situations in harbors, because I grew up by the ocean, and by bays like Chesapeake Bay. And we would sometimes see fish populations get so high due to an influx of food that the fish would eat their population, they eat the food so fast their population goes up so much that they actually suffocate in the water. They use up all the oxygen, and then all these fish die and suffocate, and just you get these fish kills that just decimate the population, and then the whole thing starts over again. Gosh. Food supply. You decrease the food supply, the carrying capacity drops and can even decline. Disease can take a population from here to down there. Predators, increase the predators, you decrease the predators. So any of these hands, if you release them, a population can jump up. If you push them down, add more of that, it goes down. And you can level the population. So understand carrying capacity, because in the videos by Malthus and by a fellow Roslin, we talk about this, living at the carrying capacity and what your population number is for that. So let's end with my least favorite graph. This is looking at human population from 2 million years ago, before we even look like we look like today, to about past 2000. Look at this. This is, this is billion. So that's 1 billion, guys. Look at this. It wasn't until almost 1800s that we had 1 billion people. Look how few people were in the earth many years ago. And look at this increase. Start looking at about, a few thousand years ago when agriculture started. Look what it did. It almost doubled the world's population a little from here to there. And then as we started developing technologies and started using animals for labor, look at how population went up. But I want you to notice something right here. We can start getting into more technologies. But look at this right here, and then starting here, this goes up. Now, right about here, you can say Industrial Revolution. Yes, it did lead to an increase in population, but also a decline with famine and disease. But right here, something miraculous helped the population to now skyrocket like a SpaceX ship. Can I guess? Modern medicine and sanitation, toilets and medicine. Not just availability of food. That has not really changed much. So think about toilets and medicine has allowed our population to grow at an exponential rate to the point where 2100, we might have 12 billion people. And guys, I'm going to use a term for you. I'm going to give you a year right now that you better memorize. 2050 is called the put on the brakes year. If we don't control the doubling of this growth rate, if we don't control that growth rate by 2050, we will be getting here so quickly. That means that we will be beyond the carrying capacity of the world. And that means no more children, or we're going to have to be killing each other to be able to have children, and probably we will wipe out all the resources of the earth before then, and our population will drop, maybe even to the point of extinction. So you're going to hear a lot about the 2050 scenario and why we're aiming at stopping this and stopping our carrying capacity here so we never get to the point where we deplete the earth. On that note, there is hope, and we're going to hear about that in this class. Because guys, once we're at carrying capacity, that means the rest of biodiversity will be gone. It will be a totally different earth, unlike we've ever could imagine. Goodbye.